Hi guys, I'm here to talk to you about my semester project for 496. I was basically continuing the work that Dr. Revoir did for a previous semester. And what we're doing is trying to find the power and performance signatures of high-performance computing applications. So the data we gathered was from model-specific registers. Most of you probably aren't familiar with these, but you can think of them as regular registers on a processor, except that they have a whole bunch of them that do things like power, thermal measurements, performance monitoring, a bunch of different things like that. And we collected this data with an API developed at Lawrence Livermore National Lab last summer. We call it libmsr, and it makes accessing these registers much easier, because normally it's kind of a pain in the butt. So the reason why we find power signatures of high-performance computing applications interesting is because there is a limit of how much power you can get into a building to power a supercomputer. So the current trend in supercomputing is to actually put more nodes on a supercomputer than you can power, and then just send the power where it is actually needed. And they are trying to develop a power-based allocation rather than a time-based allocation where you say, I need this node with this much power on the supercomputer rather than I need this much time on the supercomputer. So here's the supercomputer which the data for this project was collected on. It's called Catalyst. It's located at Lawrence Livermore. So what we want to know is, will this application have a consistent power and performance signature? Because if it uses a dramatically different amount of power each time, then a power-based allocation is going to be a little tricky to nail down. And this can easily happen because there's things like manufacturing variability and processors. They don't all use the same power. They don't all really run exactly at the same speed. We also want to identify where the power is needed most. So for example, we can allocate it onto the CPU, the DRAM, or the GPU, or other parts possibly. For this project, I gathered about 750 gigabytes of data because we were sampling these registers at 1 kilohertz. And a lot of these benchmarks run for quite a long time, so this quickly added up to be tons of data. But luckily we were able to compress this into statistical feature vectors, which, it's just minimum, maximum, median, things like that. The next step was to analyze our feature vectors in R using the hierarchical clustering and random forest techniques. So hierarchical clustering basically tells you what things look similar based on how far apart their feature vectors are. And then random forest uses a decision tree to and we were trying to use that to identify which application was running based on the power and performance signatures. And we were actually able to find over 90% accuracy in identifying which application was running in random forest. So here's an example of a hierarchical clustering. What this shows is the relative distance between these different benchmarks which were run. Each benchmark was run 3 times, and we also used 2 different data set sizes. And so ideally what you would want to see is that there are all the benchmarks of the same type are clustered together no matter the data set. And so you can see ones like CG and EP on the end there cluster really well. The colors here show the true clustering. And then there's some that don't cluster so well, like LU there. The same data set clusters together, but then you have the different data set over here. And then there's a third one, MG, which is all over the place. That doesn't cluster very well at all. However, we were able to get very high accuracy in random forest. And this graph here shows you the importance of the different variables we used in identifying the power and performance signatures. So for example, here, the most important one was branch misses retired median, which, if you know anything about computer architecture, you know about the branch predictor. This is basically telling you how many misses there were. And that is the median of that measurement. And we have also, as I said earlier, the standard deviation and a couple other statistical measures for each different metric. So in the future, what we want to look at is, do we need 1 kilohertz sampling? Is that actually necessary for this power signature? We also want to gather this data for other benchmarks because we only did the serial benchmark, so next we want to look at OpenMP and MPI. And we also want to look into adding more statistical measures to our feature vectors. And at this point, I'll answer any questions.
At what point do your number of decision trees basically cap out in terms of improving your statistical predictors?
So they recommend 2,000 when you use random forest, and I never really experimented with lowering that value, but increasing it to 3,000 or 4,000 did not really have any effect on the decision on random forest. Changing the mtry variable, which is the number of variables used at each fork, did have quite a bit of influence on this, though. It usually changed things up to 20% both directions. Yes.
Excuse me, what approach will you take to determine the sampling frequency necessary?
What we're going to try to do next is downsample, so to combine the data points we have into fewer data points. We could go ahead and gather all the data again using a slower sampling rate, but we don't really feel that's necessary when we can just combine the data that we do have.
Questions? Thank you so much. Welcome back. So good to see you all here. I really feel bad that we have such a so little time for each speaker. I know that every one of the speakers that you listened to last time and this time, they've spent hours and hours on their projects, and we unfortunately, because of the fact that they have limited time, kind of squeeze their whole work in just a matter of 10 minutes or less. I apologize to the students and to the faculty mentors. I know how much time has gone into this. So today we have two presentations. You already heard Scott Walker, who instantly is going to graduate school in Arizona, University of Arizona. And Matt Smith. Both of them have worked with Dr. DeBois. And Matt Smith.
All right, thank you. So I worked on, for my senior project, I worked on a 32-bit MIPS emulator in C++, which I actually started over a year ago and then rewrote. So for those of you who haven't taken 351, MIPS is, you'll only get a small subset of MIPS. This was the full instruction set architecture. You can see here there's lots of different revisions, and this was in the actual modern variety, which is much more complex. And the goal here was to implement all the non-floating point and privilege instructions, and to implement interrupts and exceptions, and virtual memory as well was the last goal. So I'll kind of blow through a lot of these slides here and give you kind of a crash course in writing an emulator, and then I'll actually try and demo it the remaining time. So CPU emulation, you don't want to, for performance reasons, you don't want to implement like a pipeline, you don't want to simulate a pipeline, so this is a simple single cycle fetch, decode, execute. So you fetch the instruction from memory, you decode it, and then you actually jump to your implementation for the instruction and execute it. And there's other techniques such as just-in-time compiling, which are much, much faster in this and also much more complex. So instruction fetch here, I won't go into the code details too much, but you can see it's very, very tightly optimized. You're calling this every single instruction. So it needs to be very, very fast. There's no address translation shown here, but that's actually in the code, and there's no word alignment checking. So, but it needs to be very, very tightly optimized. For instruction decoding, MIPS is really nice in this regard. It's a fixed length instruction. So this is different than like x86, which is variable length encoding. So you're just doing a series of bit shifting and masking. Really, really easy to get the instruction format. So opcode is the most important. Funct is also very important. And we'll see how those are actually used. So we fetched the instruction, we decoded it, now we actually need to execute it. So computed goto lets you take goto labels, which are normally considered bad programming practice, But for here, they're very important for performance. As Scott just mentioned with branch prediction, actually in his presentation, branch prediction is hugely important here. You get a lot of branch misses if you have a giant switch statement and some other techniques you can use. So what we do is you actually have a bunch of labels in a giant function and you store them into a table like this, and you use the opcode to actually index into that table, and that allows you to actually just jump to the instruction very quickly. And here you can see a couple sample instructions. The decoding is actually done kind of local to each instruction, so the opcode is decoded somewhere else, and then we'll actually decode the register fields and the immediate value and stuff like that. And you can see the actual, the instruction itself was just to add two numbers together, so it's pretty simple. And finally, the memory implementation. The virtual memory actually is a lot similar to this. So the physical memory layout was you use the top 20 bits of your address, and that indexes into a first table, which is a table of pointers. And the second table is actually a chunk of about 4 kilobytes of memory. And this allows you to avoid having to just allocate a giant like 500 megabyte array, which is really, really wasteful. This way you can actually allocate different chunks of memory on demand as they're actually addressed or stuff is loaded into them. And again, to access these tables, very, very simple. It's just some shifting and some bit masking. And now, I'll try and demo this here in the short amount of time I have. If I can find my mouse. There it is. So hopefully you guys can see this here. So, first start up, it's actually started paused. You can see there's a few, I've got a few commands here. There's actually 2 threads here, one for the CPU, one for the I/O, and they're communicating over an emulated serial port. So I'll go ahead and start it here, and hopefully, yeah, okay. So this is U-boot, which is an embedded bootloader. It's used on MIPS and ARM and a few other architectures. I think it's actually used on some smartphones. And I'll go ahead and boot ELF here, and you can see this is as far as I got with Linux actually with early boot. So right now it is actually paused, trying to read a real-time clock that I have not implemented. So it's going to sit there and keep reading it over and over forever. So that's my demo. I don't know how much time I have left. Take questions. I got 1 minute left? Yes. Okay, I can show some other things too. So you can see here I actually paused it and decoded. This is showing the decoding for that full instruction. There's actually a disassembler as well. And you can see up here, we already, just in this short amount of time, we already executed 1.2 billion instructions. So you can see how fast this all really needs to be, especially for an interpreter, which is a little bit difficult. And I'll show, I guess I can just demo interrupts real quick. You can see here, this is an interrupt test. There's a built-in count compare timer. And if I actually pause here, I can actually print that out as well. You can see the count register right here and the compare register. When the count register equals the compare register, it fires off a timer. And to show that this is actually working, I can type stuff in like hello. Oh, did I spell that wrong? Well, anyway, get the idea here. So right now, there's an interrupt service routine, and there's actually a main program, so there's a context switch going on. So I'm going to type all kinds of stuff here, and it'll actually print out. All right, any questions? Anyone? No one wants to ask how long it took to write, or the hundreds and hundreds of hours? Yeah, okay. No. Sure.
I seem to remember talking to you a while back that you used a model-specific register to look into the system call table. Is that right?
That was a different project. Yeah, that was OS's project, writing a small keylogger, basically. But yeah, that was a CR0 register. Any other questions? Yeah.
Thank you.
All right, thank you.
It's 2 wonderful talks. So we have had a number of 496s this semester. And of course, you just saw two of the 496s. 496 is capstone experience. That or 470 fulfills that particular requirement, capstone requirement. And we've had, of course, we haven't had really the time, unfortunately, the last two sessions of Colloquium to have everyone present their work. So we have talked about the fact that we have so many interesting projects that our students work on, and we need to have a forum for them to present it. So this is more information to come. The idea is that perhaps at the end of each semester we will have a different forum that where we have more time, and everyone who has worked on a project will present their project. So I just want to mention the names of those who've had 496s this semester. Nick Shively had a 496 with Dr. Ravi Kumar. Max Gomov, Dominic Nicholson, and Ruben Romandi, they had 496s with me. And of course, Matt and Scott, we just talked about, and Nathan Seeger with Dr. Lady. Did I miss anyone?
Mark?
Oh, Mark Ayala. Mark. He gave his presentation last time. I should have checked with you, Dr. Ibar. And Mark Ayala worked with Dr. Ibar. I tried to put this together off the top of my head. Thank you so much. So, my next speaker is Mark Eric Levinson.
It's funny you said Mark, because my brother's name is Mark.
But we have Eric here.
Yeah.
One of our alumnus. And we're really excited that you're here. And please go ahead and give us a sense of what it takes to
Thank you.
have a high-tech career.
Thank you very much. So while that's going, I might as well tell you about the first slide. I only have 4 slides. My name is Eric Levinson, and I graduated Sonoma State. I was attending Sonoma State between 1992 and 1996. Graduated in 1996. During that time, I was working at a company called Broderbund Software. How many of you have heard of that company? Okay. All right, and what ensued after that is pretty much the rest of this presentation. So thank you very much. It looks like it's there.
Is it?
Yeah, recovery.
Confused me.
All right, thank you.
Hopefully it'll work.
Presentation mode. All right, great. All right, so first of all, how many of you are currently employed in some kind of a high-tech field? Great. Nice show of hands, because when I was a student here, it really, high-tech was pretty much, Petaluma was like Telecom Valley. There was all these big companies like Cisco and Next Level Communications and all of that. It was a very happening area. And then around year 2000, a lot of that went away. A lot of these companies and dot-com companies completely went away, and nothing much left. But if you weren't a dot-com company, the other areas of high tech that I was in was the consumer software piece, which was Broderbund, mostly educational software. In the upper left-hand corner, you'll see my business card. Pretty much when I started there, I came in 1992. I had just started Sonoma State, and I was a computer geek. I would have a personal computer. I would write code. I would do write all sorts of fun software. Some I marketed. Some I consulted for some companies and made a dental lab software package. I mean, a couple of other things. I was really interested in computer science and everything computer related. I had switched majors too. I was originally a EE major, and by the time I came to Sonoma State, I had made the decision, well, electrical engineering wasn't for me. Switched to computer science. They're very closely related anyways. Science and math and all of that is pretty much the same for both of them at the time. So I come in to a company called Broderbund, working in the customer support department. So this is the department. My job was basically sitting at a telephone. We had about 60 reps there, and if you had problems installing your software, which at that time was either DOS or Windows 3.0, if any of you can remember that, and all sorts of issues would ensue with that. Interrupt conflicts, printer problems. There was not much hardware abstraction or operating system device. You know, there were all sorts of interdependencies, and especially on the DOS side, everything was pretty much, you know, built up over time and made one messy operating system. But hey, that was the one that that was the most popular and that was the most used. So I started off in this career, and one thing I learned early is that if you're in your career and you're doing what your job is, and you keep doing that and you're happy with that, that's fine. If you want to go places and you want to move up, and maybe at some point get a leadership role, you have to do other things. And early on, I kind of heard things going around in the groups and in the IT group of projects that they were working on, and I started to get involved. I started to push myself into them. And basically I'm telling them, hey, I'm going to college, I'm getting a computer science degree. The policy at Broderbund was they would not hire you into any engineering or IT or computer science departments unless you had a degree. So obviously I was working on that at the same time that I was employed at Broderbund. Started out as a senior support tool specialist. We had a system inside the company that was called CDR Express. It was made by a company called Inference Corporation. They were in Novato. They're long since gone. But what they were was it was a search engine. It was using a forward chaining expert system written in Lisp. It was a full-on back office application, and you could search for problems, and you answer a couple of questions, and it gives you the answer. So my task was to manage this system and manage the cases that are in there and all the questions and all the content that was in there. And all of our help desk people, all the customer service reps that would answer the phones would use this system when a customer would call in. Now remember, this was, you know, the World Wide Web was invented in 1992. That's right when I started there, and I'll never forget the excitement when it went on, especially at Sonoma State, when that first web server was launched, and people were saying, wow, this is going to be the next biggest thing. 1995 rolls around at Broderbund, and they don't have a website yet. And they didn't need one. The big thing was, they said, well, you know, why do we need a website? We don't have money to spend on it. We're certainly not going to spend all this money just to stick some page up for people to see us. And if we did something like that, it would have to generate revenue to pay for itself. So the company was really reluctant to have a website in 1992, 93, 94. Finally, in 95, they started experimenting and trying to figure out, well, what would we have on our web? What are the kind of things that we would want to put on the website? Immediately, that whole project went to the marketing department, because we all know that marketing departments build great websites. So that's where it went. And The customer service, the whole customer service department that answered phones was part of the marketing department. And after every technical support call, we were required to upsell. We were required to say, okay, well, now that we fixed this problem, would you like to buy Mist? Or would you like to buy Carmen in San Diego? Or something like that. We would have to say. I was also managing a BBS. How many of you know what a BBS is? Great. So a long time ago, before the internet, there were these bulletin board systems you could dial into. We had a 32-line Galacticom BBS system that our computer geeks at that time, customers could call in and there were bulletin boards and so forth. At that time, a couple of us, sysops that managed this BBS, were pushing the company and saying, hey, we got to get some kind of a web presence. And sure enough, in 1995, we got that web presence. At the same time, I was involved in two key projects that I had started and needed funding and support for. The first project was something called the CasePoint Web Server client. CasePoint Web Server. And this was a tool that we used internally, that CBR Express tool, internal. We actually put it on the web. So we're talking about a forward chaining expert system that runs in Lisp, that runs on the web under Solaris. And thinking about all the technologies going into this at the time, we're like, we don't know if this is going to work or if it's going to be, how well it's going to proceed by the public. Essentially, it was one of the best technical support systems ever. We won numerous awards. We had Dell, Compaq, Skywalker, they all came out, Lucasfilms, they all came out to Broderbund to see how we did this. And they actually branded this system for their own sites at that time. So essentially the way the system would work would be, you'd have a page of all of the products. There would be, the graphics there. You could just click on it. And then you click on your operating system, Mac or Windows 3.1. You type in what your problem is. And it doesn't show it here, but it asks you a series of questions that are all weighted based on how relevant they are. And those, after you answer 2 or 3 questions, like what version of operating system, what type of printing problem you're having, it would give you your answer. And guess what? 99% of the time, that was the answer. So if you compare something like this with going on Google, 2 completely different things. This system is the data that's in the system is highly classified and organized, and I believe at the time there were like 1,600 cases, so each case was thoroughly reviewed by a human and put into that database with the relevant questions and relevant weightings, and then the actual solutions were tested. We put them all through QA and we made sure that everything worked as we said on a whole bunch of different kinds of systems. The manager at the time of the department was invited to fly all over the world and show this off at all of the various things. Yes, hi, okay. So that's this. 2 more minutes? You're good? 2 more. Okay. There was also another project where we had a system that would allow you to fax documents. So you'd give a customer a phone number, they would dial that phone number, type in a document code, and we would fax them back their solution based on that document code. One of the other sides of this CasePoint Web Server is that it was a knowledge base, and if the customer wanted to, they could type in a number into the system and a phone number, and it would fax them, because fax was still a big thing then. It would fax them the solution if they didn't have a printer or something like that. Also, if they were on the phone with a rep, they could give that rep their phone number and it would automatically fax them. That interface The company had originally quoted $150,000 for a consulting company to make. I heard that, and I'm like, this is ridiculous. I did the interface over a weekend. It was a really simple thing. It was creating a small flat file and putting it on a server. It had to be formatted the correct way. So a whole series of these things while I was at this company allowed me to really take off in my career. By the time I finished, and this is all the same company, by the way, just different names. By the time I finished, I was an enterprise systems manager, so I was in charge of all of the enterprise systems for the company. And then the company decided to move to San Francisco from Nevada, where they were. So that was a bit of a burden of commuting, but I lucked out and I found a job at a company called Turin Networks in Petaluma, which they were absorbed by Dell recently. But we had through so many mergers and acquisitions through this whole thing. There were about 30 total mergers and acquisitions. And you can read up all about it, particularly the learning company and the Mattel pieces, because there was a lot of lawsuits and stuff that ensued during that acquisition. Here's my contact information. If I know 15 minutes doesn't do us justice, but here's my contact information if anybody's interested in finding out more, or if you have a particular scenario at your job and you want to understand, think about what you want to, what you need to do. If you want to ask me how can you advance, feel free and contact me. Are there any questions? Yes.
How did you get from Turin Networks to Calyx?
So Turin went through several mergers, and in 2008 they were acquired by Force 10 Networks, and then later on Dell bought Force 10. But in 2008, while that was happening, or 2008, the whole real estate financial crisis hit. Turin lost half of their workers, including me. So I was essentially laid off. That was my first layoff in my whole 25 years career. So it was pretty devastating. But I took a consulting job and then later on found Calyx, just literally about 2 miles away from each other. And I am in charge of all the enterprise applications, just like at Riverdeep. So the production support side, the design and engineering of solutions and enhancements, and all of that. So good question. So I'm at Calyx now, and Calyx is growing. Calyx is doing really good. They're one of the few, probably the only broadband access company that builds access equipment that's left in that area. There's Adtran is our other major competitor, but that's about it. Any other questions?
So if our students were in need of internships, are there opportunities?
Yes, there are. We do have a limited number of internships throughout the whole company. In our specific IT group, I think they're looking for one right now. And I could definitely get that information to SSU.
That'd be great.
Unfortunately, most of the company now is in our San Jose office. So it's possible there might be some travel involved to San Jose. Our finance department and the rest of the group that I'm in is in San Jose. I'm actually the only one in my group of about 8 people that's in Petaluma. But ironically, the headquarters is in Petaluma, so that's where you want your support staff.
Thank you.
Thank you.
There's still some pizza left. Hold on, pizza. We're making up for last week, by the way. So our next segment is with distinction awards. So I'm sure at least you're aware that distinction awards go to people who have GPAs of 3.0 or higher, have gathered a deeper understanding of computer science topics than we present in any single course. So their understanding transcends each single course. And also perform some sort of service to the department. And it's surprising that the last requirement is really gets in the way of many others who qualify the first two categories. We have surprisingly, we have a large number of our students who are on the dean's list every semester. We're the second highest in the School of Science and Technology, even though we're not at all close to, well, we're kind of more than half if you order departments by their that majors. So we're a bigger department, but definitely not the biggest. Kinesiology, biology, these departments are much larger than ours. Anyway, it is my pleasure to present these awards, the distinction awards, and what I'm really saying is to those who still are going to be with us next semester and the following semester, that the ticket to this, we know that we have a lot of good students. Please get involved somehow in a service to help with the department. And of course, one of these important aspects of this is, for example, being a member of 7 RICS or Computer Science Club. Okay? Mark Ayala. So please go back to your seat, but then don't go too far. We're going to gather once at the very end, just so you can see how many people we have here. Maxim Gomov. Congratulations. Brett Granwood. The Roomba. It's yours. Cameron Hall. He has a class, and he was not going to miss that class because he did not want to not graduate.
Too many times.
Daniel Holtz. Mackenzie Larson. Sean McKinley. Kelly Morales. Dominic Nicholson. Philip Plummer. Ruben Romani. Forrest Rossetti. Nicholas Rowan. Nathan Seeger. He's interviewing. That's not a bad place to be. Matthew Smith.
Thank you.
Scott Walker. Mallory Walsh. Please come out back up here for pictures. So, not being able to fit in one picture is a good problem to have. Only the CS department.
Ready?
Okay.
Ready, just in case it blinked.
Nope, looks good.
Okay, everybody close your eyes so you can take another one with everybody.
Thank you.
You guys probably.
And make us all
Absolutely. Dr. Plants has an announcement.
I think most of you in here have used my textbook in 252. And if you're not aware, I'm working on an ARM version of it. And I'm about halfway through, and it's on my website. You guys know where my website is, bob.cis. Down at the bottom, it says, click here, there's a link to it. And if you want to check that out, and in particular, if you find mistakes or typos or anything you find that's difficult to understand, if you let me know, I'd really appreciate it. And this is an ongoing project. As I said, I'm about halfway through, and probably I'm guessing in another month or two I'll be finished with it. So I'd love your feedback on that if you have the time. Thank you. Oh, it's using the Raspberry Pi.
So, the semester is over, and I want to thank our students, the first and foremost, our students, for being so gracious. I know that we don't always have enough seats for students to get in, and I know that there are times that you need more help than we are able to offer. You need more lab space than we have to offer. I really appreciate the fact that you're very gracious about it. Thank you so much. I want to thank the faculty for the wonderful work that they do. It's amazing that the size of our department has tripled since 4 years ago. And we still have the same faculty, except for German, our new tenure-track faculty, and Mark Gondry next year. And we're grateful that German is here and Mark is going to join us, but it's amazing that the same faculty in the department are running the same department that's now triple in size. You can imagine how much work goes into doing that. I am grateful. Roger May. We are grateful for the work he does. He keeps us running in the morning, in the evening, in the middle of the night. And we're still looking for something to fall apart, and it doesn't. Really, And one thing about Roger is we have 3 labs downstairs, and of course we have the server room. Some of you may have seen the server room in the back, with the number of servers that we have, and we are going to have a new lab. And he manages all of that facility by himself. He gets very little help from Grace and Blanks, but otherwise, it really is, I say that really is very limited help. It's all in his shoulders, and we're grateful, Roger, for the great work you do. And Liz Pittman, who keeps the department running at the front desk. We are grateful again for her being there and for helping our students. Thank you so much. Wish you the best. Wish you luck on your exams and a wonderful summer ahead. Thank you.